What's so special about the Gaussian? Why is it the central limit, at least in the scaling and under the assumptions that we've seen so far? There are a number of ways we can answer that question, but one of them that will lead us to a more general central limit theorem is infinite divisibility. A probability measure on the real line is called infinitely divisible if it has an nth root for every n with respect to convolution. That is, for every n, there is a probability measure mu n on the real line, such that mu is the n-fold convolution product of mu n. That is, this is mu n convolved with mu n times. Now we can rephrase that in at least two equivalent ways. We can think of these as the laws of some random variables, in which case the convolution here is the sum of n IID copies of that random variable. So a measure mu is infinitely divisible if for each n there is a collection xnk, k ranging from 1 up to n, of IID random variables such that the sum of those IID variables has mu as its distribution. And then equivalently, using the uniqueness characterization of characteristic functions and measures, a measure mu is infinitely divisible if and only if there exists a non-constant characteristic function, phi n, for each n, so that the Fourier transform of the measure mu is the nth power of that characteristic function, phi n. Indeed, this is the characteristic function of this, if phi n is the Fourier transform of mu n. So let's look at a few examples. If we fix a non-negative number, sigma squared, and take independent normals of variance sigma squared over n, then the sum of those n independent identically distributed normals is a normal of variance sigma squared, as we've computed before. Since we can do that for every n, that means that a centered normal random variable of any variance is infinitely divisible. Now, just for good measure, let's see in a different way why this is true, now having the technology of characteristic functions to help us. Let's call this sum Sn. Our assumption here is that the random variable xnk has its distribution a normal of variance sigma squared over n and mean 0. By the scaling properties of Gaussians, that's the same as saying that it's the same in distribution as sigma over root n z, where z is a standard normal random variable. Therefore, the characteristic function of the random variable xnk is the same as the characteristic function of z at the scaled variable. But we know the characteristic function of z, it's e to the minus c squared over 2, and so scaling that, we get e to the minus sigma squared over n c squared over 2. And therefore, the characteristic function of the sum of these independent random variables is the nth power of that. But of course, that's precisely e to the minus sigma squared c squared over 2, which is the characteristic function of z evaluated at sigma c, and that is the characteristic function of sigma z. And by Fourier inversion, it therefore follows that that sum, Sn, has the same distribution as sigma z, which is, in distribution, a normal of mean 0 and variance sigma squared. Similarly, we've seen before that Poisson distributions have the same property. A sum of independent Poissons is Poisson, in this case with the means being additive. So if I take n sub little n and k being Poisson lambda over n independent random variables as k ranges from 1 up to n, then the sum of those n will be a Poisson random variable of rate lambda over n times n, or rate lambda. Now we can see that again using the new characteristic function method. Since we calculated the characteristic function of the Poisson, I'll let you work that out on the back of an envelope. So this shows that centered normal distributions and in fact all normal distributions, as you can quickly work out, and Poisson distributions are infinitely divisible. And it's not a coincidence that those are the two kinds of distributions that we've seen arise in limit theorems under certain scaling regimes. Now, at the moment, it might not be so clear if there are distributions that aren't infinitely divisible. In fact, infinite divisibility seems pretty robust. For example, if I have two infinitely divisible distributions, say a Gaussian and a Poisson, then the convolution of those two will also be infinitely divisible. Why is that? Because I can decompose mu as the n-fold convolution of some measure, and I can decompose nu as the n-fold convolution of some measure. But convolution of measures on the real line is a commutative operation, and so I can just reorder these as the n-fold convolution of the convolution of mu n and nu n, which in terms of random variables is just to say if mu is the law of the sum of the x's and nu is the law of the sum of the y's, where the x's are independent and the y's are independent, and they're independent from each other, then mu star nu is the law of the sum of the x's plus the sum of the y's, which is the same as x1 plus y1 plus x2 plus y2 plus down the line to xn plus yn. So that shows how to make new infinitely divisible laws from old ones. You can also easily check that linear combinations of independent random variables with infinitely divisible distributions have infinitely divisible distributions as well. But no, not all random variables, in fact very few, are infinitely divisible. Consider this example that we've seen in recent lectures, the Rademacher distribution, which places masses at 1 and minus 1 of equal weight. We've calculated easily that the characteristic function of that distribution is the cosine function. That is not an infinitely divisible distribution. To see why not, let's suppose that you could divide it. In fact, let's suppose you could divide it by 2. Suppose that there are two independent random variables, x1 and x2, with the same distribution, such that their sum has distribution mu. Well, what can we say about this common distribution of x1 and x2? For starters, note that mu is supported in the interval from minus 1 up to 1. It's going to follow from that x1 is less than or equal to 1/2, almost surely. Why? We can just look at the probability that x1 plus x2 is bigger than 1. Well, the event that x1 plus x2 is bigger than 1 certainly contains the intersection of the two events that x1 is bigger than 1/2 and x2 is bigger than 1/2. That means that this probability is greater than or equal to the probability of that intersection, but these are independent random variables, and so the probability of that intersection is the product of the probabilities, and since they both have the same distribution, that's just the square of the probability that x1 is greater than 1/2. But x1 plus x2 has distribution mu, and mu is supported on an interval which has 1 as an upper bound. And that means that this probability is 0. So it follows that x1 is less than or equal to 1/2 with probability 1. And we can do exactly the same argument on the other side to show that x1 is greater than or equal to minus 1/2 with probability 1. So what we've shown is that these random variables, should they exist, are each almost surely bounded above by 1/2. Now the 1/2 doesn't matter to us here. What does matter is that means that the law of x1 and x2 has finite moments of all orders. But as we proved, that means that the Fourier transform of that law is C infinity. Now, if this is true, then the characteristic function of mu is the square of the characteristic function of either one of these. So that says that the cosine of xi is the square of this unknown characteristic function. Let's give it a name. Let's just call it f of xi. And what we know about that f is, in particular, it is a smooth function. Well, if it's a smooth function, then I can differentiate this equation, and I get this. So that might not look problematic on its face, but notice that the cosine of pi over 2, which is 0, must equal f at pi over 2 squared, which means that f at pi over 2 must be 0. But if I plug in pi over 2 over here, I get minus 1. And that's supposed to equal 2 times f at pi over 2, which is 0, times f prime at c. And that's a problem, because no matter what value f prime at c has, it cannot multiply by 0 to give 1. So we see from this that if there is such a function f, it certainly can't have a nice finite derivative in a neighborhood of pi over 2. In fact, there is no such function, and this measure is not infinitely divisible. In fact, it's not even square divisible. Arguments similar to this can show us that no finitely supported distribution with at least 2 points in its support can be infinitely divisible. Now, it turns out the problem of understanding in total generality what are the infinitely divisible laws is a solved problem. There is a theorem and a formula called the Lévy-Khinchine formula that completely describes them, and we may discuss that formula a little bit later. To get there, I'd like to show you now an approximation theorem for infinitely divisible laws, which will lead our way to a more general central limit theorem. And here is that theorem right now. A probability measure on the real line is infinitely divisible if and only if there is a triangular array of random variables, that is, for each n, there's this sequence xn1, xn2, up to xnm, where m depends on n, and mn goes to infinity, such that all of the random variables along each row of this triangular array are independent and identically distributed, and the sum along the row, Sn, converges weakly to a random variable with distribution mu. The point that distinguishes this from the definition of infinite divisibility is this weak convergence here. Indeed, the forward direction of this theorem is essentially trivial. If mu is infinitely divisible, that means that we can find such a triangular array, xnk, k ranging from 1 up to n, IID, such that the sum has distribution equal to mu. So it's not just that it converges weakly to mu, it's actually equal for each n. The converse is a little trickier. The first step in the proof would be to show that we can replace mn by n in this theorem. That is, if there exists such a triangular array for any sequence mn going to infinity, then we can find another such sequence where the length of each row is exactly n. We're going to skip this calculation. It involves some fairly detailed tail-bound estimates that I'd rather not get into. And so we're only going to prove the theorem in the case where mn is equal to n. So suppose that we have such a triangular array where the nth row has length n. We need to construct somehow out of that triangular array for each L a collection of L IID random variables whose sum has distribution equal to mu. The way we'll do that is to consider the row of length n times L in the triangular array. Fix any natural number L and consider the sum up to NL. What we're going to do is break up this sum into L pieces. The first n, and then the next n, and then the next n, all the way down the line. So that is, this Sni here is this sum. Now notice by the grouping lemma that since all of the terms in this big sum are independent from each other, the Sni's are independent from each other for I ranging from 1 up to L. And similarly, since each Sni is a sum of n IID random variables, we get that the Sni's are also each identically distributed. The law of Sni is the n-fold convolution of the laws here, and all of those have the same distribution. Therefore, the Sni each have the same distribution for I between 1 and L. Now, by assumption, the sum Sn converges weakly to x, where x is a random variable with law mu. And so, of course, the subsequence S and L also converges as n goes to infinity, weakly to x. Any weakly convergent sequence of laws is tight. And so this forms a tight sequence of laws. In other words, we can make this supremum over all n of the probability that Sn lies outside the ball of radius r. We can make that as small as we like by choosing r large enough. Now, note also that this, as a function of r, is decreasing. And so putting those two observations together, what we actually have is that this function of r is bounded above by some function epsilon of r, which decreases to 0 as r goes to infinity. That's an equivalent formulation of tightness for probability measures on the real line. Now, using this, note that the probability that all of the terms in this sum, Sn1, Sn2, up to Snl, are bigger than r, is less than or equal to the probability that the sum of all of them together is bigger than Lr, simply because the intersection of all of those events is contained in the event that the sum of all of those terms together is bigger than the sum of r, L times. Now, if a number is bigger than Lr, then so is its absolute value. And we know that that's less than or equal to this function here, epsilon of Lr. But also, by the independence of the Sn's and their identical distribution, this probability is the same as the nth power of the probability that Sn1 is bigger than r. An entirely analogous argument, like we did 2 slides ago, shows that the probability that minus Sn1 is bigger than r to the nth power is less than or equal to that same epsilon of Lr. And putting those two together shows us that the probability that the absolute value of Sn1 is bigger than r is less than or equal to epsilon of Lr to the nth root. Since epsilon of r goes to 0 as r goes to infinity, for fixed L, this also goes to 0 as r goes to infinity. And what that means is that we've just shown that the sequence of laws of the Sni, as n goes to infinity, is tight for each I. Once we have tightness, thanks to Helly or Prokhorov, we have a weakly convergent subsequence. So it follows that there is a subsequence of indices, nj, so that S1 nj converges weakly to some random variable. Now, because weak convergence is a statement about laws, and because these guys are independent and identically distributed, that means that we can construct y1 through yl all with that same law of y here, and all independent, so that S1 nj converges to y1, S2 nj converges to y2, and so on down the line until the nth one. But that means that along that subsequence, if we take the sum Snjl, that's the sum of the Snji's, I ranging from 1 up to L, and I claim that that will converge weakly to the sum of y1 through yl. Why is that? Why does weak convergence work nicely with independent sums? Well, one easy way to see that is again from the continuity theorem. If we take the characteristic function of this sum, because the Snji's are independent for the different i's, that's just the characteristic function of the first one times the characteristic function of the second one, down the line times the characteristic function of the nth one. Now, since each of these random variables converges weakly to the appropriate y, it follows that each of these characteristic functions converges, as j goes to infinity, pointwise to the characteristic function of the appropriate y. And if I have L sequences of functions that each converge, then their product converges to the product. But the product of those, by the independence of the y's, is the characteristic function of the sum of the y's. And now, by the continuity theorem, since the characteristic function of the sum converges to the characteristic function of that sum, it follows that this sequence of random variables converges to that sum of random variables. Great, but remember, SNL, as n goes to infinity, converges weakly to x by construction. And that means that along this subsequence, we also get weak convergence to x, and that tells us precisely that x has distribution y1 plus yl. Since these are IID, and we did this for any L, it follows that the distribution of x is infinitely divisible, as claimed. Now, it seems like we used independence and identical distribution of the terms along each row of this triangular array in a fundamental way in several places in this proof. It turns out that they weren't strictly necessary. We can actually replace this theorem with an even stronger one, that is, with even weaker conditions, where we have a triangular array where the terms along each row are neither independent nor identically distributed. But we can't put just any old random variables there. There has to be some amount of near independence and uniformity of distribution in the limit in order for this to hold true. Next time we're going to explore some conditions, in particular the Lindbergh condition on uniformity of non-identically distributed random variables, and show how these conditions lead to a more general central limit theorem and eventually to a more general description of what kinds of limits are infinitely divisible.